Welcome, everyone. Today, we're diving into one of the most persistent challenges in laser powder bed fusion, mastering overhangs and support-free fabrication. Before we get started, if you are looking to stay at the forefront of additive manufacturing technology, please make sure to subscribe for more expert-level deep dives. Our goal today is to show how we can move beyond the standard 45-degree empirical limit through advanced parameter optimization and sensor fusion to finally achieve a truly born-qualified component. We start with the why. Support structures aren't just a design nuisance, they are an economic bottleneck. They account for nearly half of your total manufacturing expense. Even worse, manual or CNC removal drives 60 to 70% of your post-processing costs. Beyond cost, we face hard geometric constraints. Internal cooling channels, like the one shown here, are physically impossible to support if you ever intend to clear them. We need to transition from a print and inspect mindset to one where the part is qualified the moment the build ends. To solve the overhang problem, we have to understand the physics of the powder bed. Solid metal is an excellent conductor, but loose powder acts as a thermal insulator, possessing only about 5% of the conductivity of the solid part. As we approach the 45-degree threshold, the conductive heat path narrows significantly, trapping energy and intensifying localized overheating. This trapped heat causes the melt pool to transform into what we call the inverted mushroom. In this state, the sagging zone extends deep into the powder bed. We see three primary failure modes here: keyhole mode melting due to excessive heat, surface tension spreading the pool horizontally, and powder adhesion, where semi-sintered particles ruin your surface roughness, RA. Overheating isn't the only threat. The cyclic heating and cooling of these overhangs induce intense type 1 and 2 residual stresses. This leads to super elevation, where the part curls upward. For practitioners, the critical threshold is the programmed layer thickness, for instance, 40 microns. Once a part protrudes more than 40 microns above the powder bed, you are at high risk for a Recoater collision, which can lead to layer delamination or total build failure. How do we fight this? Through targeted parameter sets. We differentiate the core region, optimized for high density, from the downskin region, optimized for surface quality. The primary strategy here is lowering the volumetric energy density, VED. A highly effective technique is applying a positive laser defocus, increasing the spot diameter to create a wider, shallower magma gradient, which prevents dross and deep melting. We also need to rethink our scanning logic. Transverse scanning traps heat at the edge, but longitudinal scanning creates a conductive heat path from the melt pool back into the solid part. To manage the resulting stress, we recommend interlayer rotation, often at 67 degrees, and extending cooling delays between layers to allow for proper thermal dissipation. On the monitoring side, we use a suite of eyes. Near-infrared NIR tomography identifies hotspots, which signal dross risk, and cold spots, which indicate lack of fusion voids. By using sensor fusion to correlate spatter intensity with melt pool stability, we can predict defects before they are buried by the next layer. To catch what cameras miss, we look at acoustic emission, AE, and profilometry. AE sensors detect the elastic waves of subsurface cracking or delamination in real time. Meanwhile, fringe projection profilometry creates a 3D topographic map of every layer, triggering a super elevation alert and a safety stop if the part height exceeds Recoater clearance. All this data feeds into our digital brain. Using UNet segmentation models, we can perform pixel-level classification to distinguish between normal print area, powder, and defects. Platforms like Peregrine enable Flaw Triage, allowing the system to distinguish between harmless process noise and critical defects that require build termination. The industry is already racing to zero-degree overhangs. EOS's Smart Fusion uses closed-loop power adjustment to hit 20 degrees. SLM Solutions Free Float uses vector optimization for 5 to 10 degree spans, and Velo 3D utilizes a non-contact recoater to achieve true horizontal, 0-degree overhangs. You cannot manage what you cannot measure. We use standardized overhang shapes, triangles, ellipses, and circles to calibrate our digital twins. We verify success by measuring surface roughness against the overhang angle and testing tensile strength using dog bone bridge artifacts. In conclusion, the mastery of LPBF isn't about avoiding overhangs. It's about controlling the physics that create them. By closing the loop between fabrication, characterization, and property prediction, we can finally replace destructive testing with reliable in-process data. To wrap up, I've provided a list of the core studies and industrial reports that inform this presentation. For those who want to deep dive into the specific data or explore our full bibliography, please check out the references in the description below. Mastering these complexities is a community effort. Make sure you're subscribed so you don't miss our upcoming deep dives. Thank you for your time, and I look forward to your comments.